It takes energy to turn some solid into liquid, and then to turn liquid into gas. There has to be some heat added, or there has to be a gain in enthalpy for these processes to occur. The reason for this is that to turn solid into liquid, and then especially to turn liquid into gas, involves breaking intermolecular interactions. For example, to go ahead and melt water involves the heat of fusion of water. It's generally in kilojoules per mole of water, and that is just the heat to decrease the number of hydrogen bonds from the number of hydrogen bonds within a solid to the number of hydrogen bonds within liquid water. But then to turn liquid into gas, that breaks all of the hydrogen bonds between water particles because now the water particles are flying about as gas far apart from each other. And breaking all of those hydrogen bonds involves a great heat. That's the heat of vaporization. Now this is significantly higher. Heat of vaporization for water is 40.7 kilojoules per mole, whereas the heat of fusion for water is only 6.01 kilojoules per mole. Now, what about the heat of turning solid into gas, the heat of sublimation? That is actually the combination of the heat of fusion and heat of vaporization. 40.7 plus 6.01. The heat of sublimation is 47 kilojoules per mole for water. This should make sense by Hess's law. We know that the heat of a process to go from solid to gas, for example, is the same whether it's in one step or in multiple steps. So, you see a couple terms here. Heat of fusion is really just another word for the heat to melt something. Heat of vaporization, heat of sublimation. We also have condensation. The heat of that, to go from gas to liquid, is the same in magnitude as the heat of vaporization, but it's opposite in sign, going lower in enthalpy. Hence, it's the negative of the heat of vaporization. We also have heat of freezing, or actually heat to freeze something, which is the same magnitude as heat of fusion, yet opposite in sign. Finally, you probably haven't seen this term before. Deposition, or vapor deposition, is to turn a gas into a solid. So, strangest terms here: heat of fusion, melting; sublimation, deposition. So, being that it requires energy to separate these particles, it can also release energy to bring them back together. So, for example, say that you have a glass of ice-cold water. It's cold here. Now, that means that heat can flow from the air to that lower temperature glass, and when doing so, that heat, or that air, it cools down in temperature. And similarly, heat is removed from the gaseous water so that it can turn from gas into liquid. It's an exothermic process. It releases heat to turn gas into liquid. Water can condense from the air onto a cold excuse me, a cold surface. And then also, we have here sweat. You have high temperature here on your skin, cooler temperature outside. This high temperature releases heat to water, and that water, that liquid water on your skin, can vaporize. And in doing so, that absorbs heat from your skin, thereby cooling it down. You might have noticed that when it rains, much of the time, the temperature nearby falls. When water falls from the sky, we have liquid water on the bottom, on the ground there, which can vaporize, and when doing so, it absorbs heat from the ground and from the nearby air, cooling down the nearby things. All right, so we've got a graph here of the amount of heat added versus temperature. So consider a case where you have negative 10 degrees Celsius water, ice at negative 10 degrees Celsius, and you add heat to it. You'll see that its temperature should increase as heat is added. As we go to the right, the temperature does go up. However, at some point, the temperature is no longer changing. As you continually add heat, the temperature doesn't change. Where is that heat going? the heat is now going just to the breaking of hydrogen bonds, which is allowing for fusion or melting of that water. And then we can see that, again, once all the water then is melted, once we've turned from 100% solid to 100% liquid, the water can increase temperature again as heat is added until we again get to a change in state where we start changing from 100% liquid to gas. This involves the heat of vaporization. So while you're boiling this liquid water, its temperature remains constant until eventually it's all gas, and then it can increase in temperature again. So, summarizing point here, we can see that when we have a mixture of solid and liquid, or liquid and gas, when it's part of both states of matter, then any additional heat being added or removed does not result in temperature change. AKA, when you're boiling water, no matter how much remains, whether a lot or little, that liquid water there is 100 degrees Celsius. And then we have, no matter how much ice versus liquid water you have, as long as you've reached a point of equilibrium, that water is going to be 0 degrees Celsius. And so we can see that, why should you have your heat setting on high, whereas medium should allow your water to boil when you're boiling pasta? Why waste temperature or heat? In both cases, the water is going to be 100 degrees Celsius. And then whether you have a lot of ice or a little bit of ice, once you reach equilibrium, that water is going to be 0 degrees Celsius. So why have too much ice? Darn it, fast food restaurant with all of the ice. You might have to do calculations, which involve, what amount of heat is required to take negative 10 degrees Celsius water to 110 degrees Celsius. So first, you've got Q is equal to ms delta T for just changes in temperature. Delta T changes in temperature, how much heat is required for a certain mass and a certain specific heat. But also you have to account for other things like the heat of fusion, which is generally in kilojoules per mole or gram. So in order to do that long problem, you might say how much heat is required to take negative 10 degree water to 0 degrees. So that's Q is equal to ms delta T once. And then how much heat is required to take that ice to all water with no temperature change. The number of kilojoules per mole multiplied by the number of moles might give us the number of kilojoules. And then Q is equal to ms delta T again for the temperature change, kilojoules per mole times moles again for heat of vaporization, and then Q is equal to ms delta T for the temperature change again. Thanks for watching, guys.